In this video, I want to explain some of our reasoning of why we went with this type of drivetrain over the alternatives and why we went with these size wheels. Now, as you can see on our drivetrain, we have 4 wheels in each corner. The 2 back ones are mounted vertically to our orientation, and the front ones are mounted horizontally or in the x-axis. Now, the reason we went with Omni instead of something like Swerve or Mecanum is because compared to Swerve has a lot of power and a lot of speed. However, in this competition, you don't really need speed or power. It's more advantageous to be able to go in any arbitrary direction at any time over having the power to outpush another robot. So that's why we specifically went with an Omni wheel type of drivetrain, and the reason we went with this type of drivetrain is because it gave us the profile we were looking for. Now, we knew we wanted to use some bigger wheels because with some smaller wheels, it'd be very difficult to get over this ramp. We've run into that type of issue a lot in previous years where we've had smaller wheels, and even a half-inch ledge of carpeting was trouble getting over. So that's the reason why we went with bigger wheels over small wheels, is simply to make it easier to get over the ramp. We don't really ever have to do that in competition. We're pretty much just in this zone right here, but we took it into the design criteria and made it work for that. So that's why we went with those size wheels over bigger ones or smaller ones. I guess we could go bigger, but that's excessive, but specifically over the smaller ones. Now, the reason we went with this geometry is simply because it gives us the profile that we wanted. There were certain dimension constraints we had to fit into, and actually right now we're bigger than our transport configuration is. From the edge of this wheel to the edge of this wheel, we're about half an inch bigger. So what we actually have to do is we have to take off one of these wheels to meet the transport configuration criteria. But otherwise, it's not that big of a deal. Now, the tricky thing about this drivetrain is it's not a problem looking at it if you want to drive forward. You just apply the same power to these 2 wheels, and it'll drive forward and backward. However, when you move sideways, the application of sideways force is in this axis, but there's a resistance of these 2 wheels in this axis. So with the 2 axes being in different planes, there's a tendency for it to want to rotate. So when you go this way, with resistance counteracting it this way, the robot's going to have a tendency to want to turn continuously like that around the application of force. The resistance is here, the force is here, it'll rotate somewhere between there. Now, you can actually compensate for this either with a hard value or with a PID active feedback control system. We can utilize both. For what we do mainly for teleop is we just have a hard-coded value. So there's a value, a multiplier rather, so when you go sideways, it takes the sideways value, applies a certain factor to it, and applies a rotation to these back 2 wheels. So when you move sideways at full power, these 2 wheels will try to rotate the robot to compensate for it. And same thing the other way. If you try to move that way, the wheels will try to compensate going that way. And obviously, by using the opposite pair of wheels for the rotation, it doesn't affect the driver's control of moving it sideways. So the driver still has full control over the speed and distance of moving the robot, since the actual driven wheels by the driver are not the driven wheels by the compensation, and the compensation wheels will not interfere with the driver's control. What we've run into before is if you try to compensate on the wheels the driver actually directly controls, sometimes they'll be fighting each other. The driver will try to compensate the compensation, which is sometimes an issue. So with that being said, doing all these maneuvers it allows us to go sideways, as I just explained, forward and backward, and then with a combination of the 2, with basic trigonometry, you could actually make it go in any direction. So if these 2 motors are full force that way, these 2 are full force that way, it'll have a tendency to go 45 degrees. But again, as I mentioned, due to the fact that it'll have a tendency to rotate that way, this wheel is actually slowed down. So we want to go this way, that wheel is at full power, these 2 wheels are at full power, and this wheel is being slowed down slightly to apply resistance this way. So then with that force vector, it's going to go actually at 45 degrees. And again, the other way to do it, which is a combination of what I do, is use active feedback PID control to keep its orientation locked. And you could either use a gyro or a compass or some other IMU system to give you an external heading. So as the robot rotates, it has a reference heading, and it could automatically apply a counter rotation to always keep it locked to that orientation. So there's still different approaches you can take to actually maintain your heading, but that's just some of the approaches we've taken, and it seems to work well enough for us. Other than that, that's pretty much it in regards to this drive base. The only other thing I want to mention is the way the drivers actually control this is the drivers never actually, quote-unquote, steer the robot. The robot will go wherever the joystick is pointing, regardless of the robot's orientation. I think it's called off-robot steering, and I could demonstrate that real quick. So you see the robot is sideways, so when you push sideways, it goes sideways. And see how it maintains its orientation simply by the value. However, if you rotate the robot, let's say like this, and then when you go to the right, it still goes to the right. So it doesn't matter which way the robot is facing, wherever you point on the joystick, that's the way the robot will go. So even at this angle, when I press forward, it's going to go that way. Now sometimes it does have a tendency to want to align itself, but that's no big deal because the driver can actively rotate, compensate for it. So as I pull back, the robot will come towards me. Again, it will rotate, but that's really not much of an issue. So that's one issue we do have with this bot, is we can't get over it sideways. So if we're like this, we cannot go over that ramp. We actually get stuck. If we want to go over the ramp, we have to do it either in this configuration or in this configuration. So, no problem. All right, hope that helped somebody. See you next time.